Right, I'm going to talk now about data compression, and the specific technique that we're going to look at, it will be Huffmann coding. Okay, and what exactly is meant by compression? Okay, so I'm just going to explain very informally. So compression is whereby you try to reduce the size of a particular file or particular set of data. Okay, and what kind of data that we are going to look at? So we're just going to look at text data. Okay, so assume that we are given as input a sequence of strings. So we're going to look at an example here. Right, suppose we're given this input text, okay? Data compression, Huffmann coding, Huffmann data, and so on and so forth. And okay, so each of these strings, okay, they will need storage, okay, they will need space for storage. Okay, so for example, consider the word data, for example, okay, just this particular string. Okay, assuming that each alphabet is stored using some kind of an ASCII representation, and okay, suppose that is 4 bits per character, so it means that just this particular string data that will need 4 times 4 bits. Okay, so you can imagine that in all, okay, we need a substantial number of bits, okay, to store all this sequence of strings. So the idea in compression is to reduce the number of bits needed to store this same data, right? Okay, now the basic strategy in data compression is to replace the string here with a particular code. So for example, okay, look at this data, string data, and okay, what we are doing here is that we are replacing it with 0, 0, 1. Okay, can you see that? And compression, the string compression, we replace it, or we encode it with the binary string 1, 0, 0. And instances of the same string will replace it with the same code. So for example, here we have data, and data is replaced here with 0, 0, 1, similar to what we have for the first instance of data. Now, doing it in this way, we can see that there will be a vast reduction in space requirements. So for example, had we stored data using something like ASCII, something the like, that will need something like 4 times 4, right? We saw that earlier, so that is equals to 16 bits. But here, it's possible to store 001 using just 3 bits. So that is way better compared to the original 16 bits. In fact, we don't even need the spaces between the codes. So this is what we have after I delete all those codes. And so there will be further space reduction, okay, storage reduction. And of course, it's important that we be able to read back all these codes. And okay, so how do I read this? Okay, of course I need to know, okay, how the different strings have been encoded. Okay, I'm going to write it here. Okay, so data has been encoded as a 001, and compression has been encoded as 0100. Huffmann has been encoded as 011, and coding has been encoded as 010. Okay, so given this information, okay, we can translate this string of bits. Okay, this string of bits, we can translate it back to the words. So for example, okay, let's check out the first 3 bits. So it is 001, and 001 is data. So we have here data. And then following the first 3 bits, okay, we have the next 3 bits being 100 and 100 is compression. So we write here compression, and we proceed on in the same way. Okay, so this is the process of decoding, okay, translating back from the code to the original text. Okay, and there's one thing to note here is that it is possible to do the decoding in this particular example because the codes are so nice. Okay, what I mean is that okay, let's take a look here. Okay, 001 for example. Okay, one moment. Okay, yeah, 001 for example. Okay, that can only be data. Okay, 100, that can only be compression. Okay, so the codes are all unique. Okay, there's only one way to interpret 001. Okay, there's only one way to interpret 100, and the same goes for 011 and 010. Okay, and okay, so they're all easy to decode. But what if we have something like this? Okay, for coding, okay, instead of 010, we have something like 0010. Now, had the codes been like this, then it would be more difficult to decode the resulting what do you call that? The resulting code. Okay, the resulting compressed result. Okay, why would that be the case? Now consider 001. Okay, now it's a bit difficult because 001, it can be either data or it could be part of 0010, which means that if I read one more bits and it turns out to be 0, then the entire 4 bits correspond to coding. Okay, so it means that there will be ambiguity if we were to assume this sort of coding. Okay, can you understand this? Okay, so the difficulty that we saw in the previous slide is due to one code being a prefix of another code. So what is meant by one code being a prefix of another code is that, okay, as we saw in the previous example, okay, we have one code being 001, and we have one other code which is 0010. So 001 is a prefix of 0010. So when this happens, it will be difficult to decode the compressed text. Okay. Now here's another example. Suppose, okay, now take a look at the resulting compressed result here. Okay, so in this particular example, data has been encoded with just a single bit, which is 1. Okay, and you can imagine how difficult it is. Okay, so this is supposed to be the bit corresponding to data, and this 100 is supposed to correspond to compression. But had I not known that, it would be difficult, because should I read this as 1 or should I read this as 110? Alright, so it's important that the code we use for the compression be what we call a prefix code. Okay, which means that okay, none of the code is a prefix of something else, okay, of some other code. Okay, at this point, you're actually ready to state the goal of data compression in a manner which is a bit more formal. So what do we seek in data compression? We are trying to find, okay, we are trying to find a prefix code. Okay, what is the meaning of this? Okay, with the maximal compression rate. But first, what is the meaning of prefix code? So a prefix code is one in which there is no code which is a prefix of some other code. That's all. Okay, so I know that the naming here is a bit confusing, so maybe we should say it's as something like a prefix coding system is a coding system in which there is no code that is a prefix of some other codes, right? So for example, in the previous slide, okay, we saw this particular example, 001. Okay, this is one code representing one particular string, and then we had one other code representing another string, right? And as we saw, okay, 001, it is a prefix of this, okay, which is not good, okay, which will make it difficult to later when it comes to the decompression or the decoding. Alright, so a prefix code is one in which there is no such case. Alright, so find a prefix code with the maximal compression rate. So what is meant by the maximal compression rate? Now, earlier we saw the input text, okay, that we are using right now as an example. Right? So we saw, for example, data, okay, an input text that contains the word compression, and so on and so forth. Okay, and we noted that this requires some space, this will require some space. And we noted as well that we can encode this string data with certain bit string. So for example 001, compression for example 110. Okay, I'm just putting it an example here, right? And I might be repeating things, but never mind, I'm just trying to reinforce the concept. Okay, now, so this is 3 bits and this is 3 bits. Okay, but what if we were to represent this using just something like this, 0, 1 and 1, 1. So this is 2 bits and this is 2 bits. Okay, so it means that if we use this particular coding type, then the compression rate might potentially be high. But then again, of course, okay, we have to check, okay, whether or not the resulting coding system will be one which is prefix. Can you understand this? Okay, so the higher the compression rate, of course, it means that the lower the average code length. So as we can see here, the average for this part here is 3 and the average here is 2. More or less something, the idea is something like that, right? Okay, but we'll get to understand, you'll get to understand this as more as we go along. And it's time to be a bit more mathematical in order to be able to analyze a potential coding system. And okay, how are we going to do that? Right, so consider the text that we have been looking at. So for example, we have something like data, compression, Huffmann, and so on. Okay, now think of this as what is stated here as set of alphabets. Okay, what is meant by that is that, okay, data, okay, we shall represent that as x1. Think of it as just a symbol, okay, an alphabet. Compression, okay, it would be x2, and Huffmann, it would be x3. Okay, so any instance of data, so for example, let's say we have another data here, so this data is just an alphabet x1, right? And so this, what we have in the input text, is just a set of alphabets. Okay, so note, it's a set, not a sequence, because here we just want to look at the list of possible possible strings that appears in the text. Okay, and so each string, right? Okay, we can read this as we can understand this as that. So each string, or what we call here alphabet, okay, we just name it alphabet, because when we use x1, we just refer to it as an alphabet. Okay, but in actuality, it represents a string. So now each alphabet x1, xi, occurs with a probability pi. Okay, so this I is just an integer. It can be 0, it can be 1, 2, 3, 4, 5, and so on and so forth, such that the sum of the probability is equals to 1. Alright, so what does this mean? Okay, let's take a look at this particular example. Let's assume that this is all that we have in the input text. Okay, so this is all that we have. So how many strings do we have? We have 4 strings, right? Data occurs 2 times. Compression, it happens 1 time. And Huffmann, we are seeing it once in this particular example. So altogether we have 4 words, 4 strings. And the frequency for data, okay, the probability of seeing data here is 2 out of 4. Compression is 1 out of 4. Okay, this is basic probability, right? Huffmann is 1 over 4. Okay, and looking at all these probabilities, okay, the sum of all this, okay, it is equals to 1. Right? 2 over 4 plus 1 over 4 equals to 3 over 4. 3 over 4 plus 1 over 4 equals to 4 over 4 equals to 1. Okay, so that's what this particular statement is saying. Okay, let's consider a bigger example. Now this is the thing that we have been looking at, a complete set of what we have been looking at, right? And okay, so you can see it here. So we are going to calculate the probability for the strings in this particular text, and I've done that actually, and this is what I have. Okay, you can see it here. Okay, so the different strings that happened in this particular text, it is, alright, data, compression, Huffmann, and coding. So I count the number of occurrences for data, and it's 4, compression is 3, Huffmann is 5, and coding is 2. And the total number of strings is 14. Okay, and then I can, once I got the frequency, I can calculate the probability, which is just, okay, the number of the frequency divided by the total frequencies. So for data it is 0.29, compression is 0.21, Huffmann 0.36, and coding it is 0.14. So note that the total probability is equals to 1. And this is the mother of all formulas in data compression, in information theory. Okay, what is the meaning of this formula? Okay, I think you might have encountered this, okay, many times in data compression book, in an information theory book. Well, okay, right now, okay, what we going to understand is that, okay, the left hand side is what they call the self-information. Okay, so I means self-information, and the left hand side here, okay, we are looking at self-information of a particular string. Okay, xi is an alphabet, but it's referring to a particular string, right? Okay, equals to, okay, what is on the right hand side here. Okay, this is a log, negative log. Okay, why is it negative log? Okay, so we have to try to understand that. And k is just the base of the log. So normally k will be assumed to be 2. Okay, and again, okay, why k equals to 2? So we have to, okay, we have to try to understand that. Okay, that's normally the way they do it in textbooks and papers and so on. But okay, let's try to understand that. Okay, and pi here is of course the probability of the string corresponding to xi. Okay, so it looks, okay, it is a short formula. Okay, but what is the meaning of this? Okay, what is the meaning of this particular formula? Okay, why negative log, and why negative log probability, and why do they call it self-information? Oh. Okay, so in order to develop an understanding of, the formula, I'm going to do a numerical experiments involving the log function, and I'm doing this in Microsoft Excel. You can do it in any spreadsheet. So I have this table that I copied from this spreadsheet. So this table comprises of 2 columns. Okay, one is for the probability. Okay, so I have various values of probability in this particular column. Okay, one moment. Oops, alright. So this is P probability, and I'm trying for values of probability values of 0 until 1. Okay, and I'm going to fill up the corresponding log value here in the right hand side in the right column. Alright, and this is what I have. Okay, I have to get rid of the 0 because log 0 is not defined. Okay, and for all other values of p, and we have it here, okay, the corresponding log values, and as you can see, okay, many of these values are negative. So 0.1 log of 0.1 is negative, negative, and so on. And of course log of 1 is 0, right? Okay, so that might explain why in the self-information formula we have negative log 2. Okay, we have the negative here instead of positive log, we have negative log. Okay, so when I put in the negative in front of the log, okay, when I negate the log, this is what I have. As you can see this new column. Okay, so this is a negative log, so it's positive. It is all positive numbers, and of course for 1 it remains as 0, right? So the numbers now look nicer. Okay, so that probably explains the negative. But more importantly right now, what is the meaning of all these numbers? I'm just wondering, okay, what do they represent? Okay, what do they mean? For example, okay, if I take 0.1, right? Okay, what is the relation between 0.1 and 3.32? Well, that is something to think about. Let's think again. Okay, 0.1, 0.1, 3.32. Okay, so 0.5 correspond to 1. What does this mean? Okay, what is this? What is the meaning of this relation? Okay, 0.5. Okay, what do you understand by probability equals to 0.5? Right, when we throw a coin, a balanced coin, the probability of getting head or tail is 0.5, right? A coin, what is a coin? In the context of a binary system, what is a coin? Well, a coin is just a bit, a single bit. Now the reason is that a single bit, if you were to randomly generate its value, it will be either 0 or 1, right? The probability of 0 is 0.5, the probability of 1 is 0.5 as well. So this value 1, it might have got to do with the number of bits that we require to store events with a particular probability, right? Okay, so let's consider this now. 0.1. What is the meaning of 0.1? It's like having 10-sided coins or dice. So 0.1 is 1 over 10. Okay, and what can generate 10 possible values? Okay, so that is the question. And okay, we can do a bit of combinatorial calculation here. Okay, 1 bit can store 2 values, 2 possible values, right? 2 bits, it will be 2 times 2 values. 3 bits, it will be 8. 2 times 2 times 2 equals to 8 values, and so on and so forth. So in other words, okay, the number of values, okay, we can represent it as okay, let me do the calculation here. 2 to the power of n equals to number of values, right? So n is the number of bits. Okay, so if I want 10, that means 2n equals to 10. 10 is the number of possible values. And in order to solve this, I can just apply logarithmic mathematics, right? Logarithmic arithmetic. So this is just n equals to log 10 divided by log 2. And if you press into the calculator, you'll get this value is 3.32 something something something. In fact, a value which is the same as this. Well, we're on to something here. These values, okay, I suspect them to be related to the number of bits that you will need to store, okay, strings with the probabilities, with the corresponding probability. Okay, so we now can go back to the self-information formula armed with a new understanding of what it means, right? And okay, so we have here the self-information. Okay, self-information. So we have seen that it is related to the number of bits which is required to store a string or alphabet xi, okay, with a certain probability pi, right? Right. Okay, now I'm spelling this log as lg. So this, okay, is meant to represent log to base 2, right? So from now on, we just assume log to base 2. It's possible to use other base, for example, base 10 or base 16 and whatnot, but in the context of a binary system, the result, the outcome will make most sense if you use log to base 2. Okay? In fact, we can write it in this way now. So Li, okay, this is the length, the number of bits required, okay, and the number of bits required to represent a certain string, okay, that will be the ceiling, okay, will be round up whatever the values of negative log of the probability of that particular string. Now we have seen this before, we're just putting it in the form of a formula. Right, can you understand this? Okay, so for example, 0.5, okay, let's say pi equals to 0.5, no, not 0.5, 0.1, okay, we have seen this example, right? So log pi, this will give you negative 3.3 something, and negative log pi, this will give you 3.3 something something something. So when you take the ceiling of this, okay, when you round this up, okay, what are you going to get? You will get negative log, okay, let's say pi equals to, round it up, you'll get 4, okay, and 4 is the number of bits that you need. 1, 2, 3, 4, the number of bits that you need in order to represent this particular probability. Okay, so this is the Li value. Okay, and in the literature, in the textbook, okay, they call this Shannon length. Okay, we come now to this formula that you will meet in any textbook on compression or on information theory. Right, so this is the entropy formula. Okay, so entropy, right, and this is a summation, and you might notice that this is a summation of a weighted summation of the self-information. So what do I mean by that? Now I can rewrite this as, okay, okay, I can just expand this just to show you. Okay, so if we expand this, we have p0 here, log p0, right? And then I can keep adding up p1 plus minus p2 log p2 and so on and so forth. Okay, so the negative log p0, that is the self-information for string the alphabet 0. Okay, so in other words, we are forming the average of the self-information. Okay, so let me write this here. This is the actually the average of the self-information of the strings that we have in the input text. Right? So how to understand this? Of course, we have to look at an example. Okay, so here we look at a simple example, one that comprises of just two strings. Okay, we have, okay, so we have data. Okay, suppose the input text comprises of data and the string compression, and okay, to keep things simple, data, the probability is 0.5, and compression, the probability is 0.5. Now, what is the average, what is the entropy for this? So the entropy is Hs equals to, okay, what's the self-information for data, okay, which has a probability of 0.5. Okay, we have seen this calculation before, right? It is equals to 1, right? So 0.5, it is the probability. Can you see this? Okay, we have to multiply with the probability, right? So 0.5 times the self-information, okay, which is 1, so we have 0.5. And we do the same calculation for compression, okay, so we have 0.5 as well. So altogether we have the value 1. So that is the entropy for this particular example. Okay, so is it all clear up to now? Right, there's something that you might notice. I'm thinking about this right now. We have seen before, right, that self-information, okay, again, I clicked the wrong button, okay, self-information, which is this, okay, self-information, it is, okay, so that it is related to the number of bits, correct, and, or what they call, okay, the Shannon length. Okay, so if self-information is related to Shannon length, now it means that entropy is related to the average number of bits. Can you see this? Average number of bits. Okay, so in other words, this entropy tells us something about the average length of the code that will be needed to encode the text, the strings in the input text. Can you see this? So we can go back now again to the goal of data compression. Okay, we can restate the goal again. Right, so we can state it in a more precise form now. In data compression, what we seek is this. We seek a prefix coding system with the minimal average length for the code. Okay, so this L average means the average length of the codes that we use, right? That we need. So this is just summation. Okay, we awaited summation weighted by the probability of each length, and this probability is of course the probability of the string. Okay, so for example, okay, let's say we have something like this again. Okay, we go back to the previous example. We were looking at data and compression. Okay, so we saw that this is 0.5, 0.5, right? So what is the average length that we require here? Okay, we have seen that for data, okay, the length is the average length of the bits that will be required to represent data with the probability 0.5, right? Is 1, and the same goes for compression. Okay, so the average, the average length of the code, it shall be L average equals to, okay, probability here is 0.5 for data, right? So 0.5 times, and the L0 here is 1. Okay, so we add to the calculation for compression, okay, which is the same actually. 0.1 equals to 0.5 times 1 equals to 0.5 plus 0.5 times 1 equals to 0.5 equals to 1. Okay, so the average length of the code that is required, it will be 1 for this particularly simple example. Okay, so is it all clear? Right. There is one thing that we have to think about, that is about prefix. Okay, I highlight the word prefix here. So the question is, how do we determine if a particular code is prefix, a particular coding system is prefix? Okay, we might have something with the minimal, that gives the minimal average length, but how do we guarantee that the code is prefix? Because if it is not prefix, then regardless of the compression rate, it is useless. So we have to think about this now. Okay, let's go back to the coding system that we used in our very first example. So this is what we had then. Okay, so the strings that we had in our input text, okay, they were all this data compression Huffmann encoding with this probability, frequency, and probability, and this, okay, these were the codes that we used. So data translate to 001, compression translates to 100, and okay, so on and so forth. Right, now how could we tell whether or not this code, okay, this coding system is prefix or otherwise? Is there any way to know about this? Okay? Is there any characteristic that we can gather from this code that will tell us whether or not it is prefix code? Right, look at all these codes. They're all binary strings, right? 001, 100, 011, 010. Now, what else do we know about things binary? Okay, we have learned about binary trees. Okay, you might have heard about binary trees in one of your computer science classes, right? No. So the question that I'm thinking of right now is that can I represent all this as part? I mean, can I characterize it all with a binary tree? Okay, let's just draw a binary tree. Okay, how would a binary tree that corresponds to a binary code look like? Okay, suppose it looks something like this. Okay, so we have a node. Okay, this is the root. In fact, okay, this is the root. So to the left, okay, we label it as 0. To the right, we label it as 1. Now we continue further. This is 0 and this is 1. 0, 1. Oops, sorry. 0, 1. This is 0 and this is 1. Okay, now we do the same thing here. 0, 1. 0, 1. 0, 1. Okay, so now starting from the root, Okay, this is the root. Okay, I'm going to color it red. Right, so starting from the root, okay, the depth is at the most 3, right? So if you look at the code here, okay, the length of the codes are all at the most 3. In fact, all of them are 3s. The lengths of all of them are 3, right? Okay, now then let's take a look at this particular code 001. Okay, 001. Okay, 001 is this, correct? And 100, that will be this. And 011, okay, what is 011? 011 is this, right? Right. So okay, so what we are able to see here is that a binary tree can represent a coding system. Am I right? Okay, now what else can we tell about this binary tree? Okay, now that we have represented our coding system as a binary tree, can we extract some useful mathematical properties from it with which we can tell whether our code can or cannot be prefixed? Okay. What can we see here? Okay, now this tree is a bit complicated, right? I mean, this tree is a bit too big, and okay, so we need a simpler example. Okay, let's say our codes. Very simple example. And let's take a look at a binary tree that can house this, okay, that can hold this. So we have this sort of binary tree. This is a single level binary tree, 0 and 1. Okay? So this is enough to represent this particular code. Now, what can I tell about this? Well, okay, now let's try further example. Alright, okay, let's see here. Okay, we have this now. Codes. Okay, 0, 0, 0, 1, 1, 0, 1, 1. Okay, let's try this. 0, 1, 0, 1, 0, 1. Now, what can I tell about this binary tree? Okay, if the code is that nice, then okay, it's kind of balanced, right? The tree is kind of balanced. What do I mean by balance? Is that okay, to the left side, okay, to the left side we have 1, to the right side we have 1. Okay, I mean, okay, the codes form the codes kind of correspond to a full binary tree, correct? Okay, I mean, for this particular example, it corresponds to a full binary tree. And what can I tell about that? Okay, now okay, now suppose, okay, we think of this. We think of it this way, right? Assuming that these codes kind of have equal probability of happening, then okay, this will be, the probability will be half, and this will be half. Okay, let's not talk about probability, but just think of dividing the number 1 equally among the codes here. Okay, the codes here. So this will be half, and this will be half. Correct? Now, can I see this half in this binary tree? Well, this path forms half of the length, I mean the total number of edges, okay, in the tree, and this particular edge form half as well. Okay, right. Where do we go from here? Okay, let's look at this example here. Now 1 divided by 4 equals to a quarter. Okay, all these correspond to 1/4. Alright, and take a look at this tree here, right? So 0, 0, where is 0, 0? 0, 0 is here. How many edges do we have there? We have 2. And 2 edges, and how many possible, what is the length of all, the total length of all the possible paths? Okay, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, no. Okay, we have how many possible paths are there? Okay, 1, 2, 3, 4. So in other words, this 1/4 here correspond to 1, 2, 2. Okay, where do I get a 2? The 2 is the length of each of those paths. Okay, am I getting somewhere here? Okay, let's think of this. Okay, what are they actually? Okay, let's think again of that. Okay, so I think I can. There are each of these numbers. Each of this fraction is actually 1 over 2 L, right? Where L is the length of the code. Okay, so for example here, this is 1/4 and this is 0, 0. The length of the code here is 2. So this 1/4 corresponds to the case where L equals to 2, right? And this is half, right? The length of 0 is 1. So 1.5 here corresponds to the case where the L equals to 1. And if I think of it that way, then what can I say? Is that, alright, okay, it means that if the prefix code forms a full binary tree, then the sum of this, okay, the sum of this will be equals to 1. Okay, let me write it here. If prefix code forms a full bin tree, then the sum of 1 over 2L will be equals to 1. Alright? Does it make sense? Now let's challenge this statement with more examples of prefix code. Okay, now suppose we have this codes. Okay, it will be two bits codes as well. Okay, 0, 0. Okay, but let's just stop here. 0, 1. Oh no, let's stop here. 1, 0. Okay. So in our initial example, we have 4 strings, right? 4 codes, but here we have only 3. Right. Okay. So this is like we have this, and this only, right? Okay, in this particular binary tree. Okay, and if I apply this formula, what will I get? Okay, so 1 over 2, 2 plus 1 over 2, 2 plus 1 over 2, 2. I shall get, okay, 3/4. Okay, so it's not equals to 1, but it's less than 1. What do I see here? Now let's try with a non-prefix code. Okay, what will be the case for a non-prefix code? Okay, what about this particular case? Okay, non-prefix, I'll just put here 0, 0, 0, 1, 1, 0, 1, 0, 0. Okay, this is non-prefix because this particular code is a prefix of the last one, right? Okay, applying this formula, okay, just calculating this summation. So I have 1 over 2, 2 plus 1 over 2, 2 plus 1 over 2, 2 plus 1 over 2, 3. Okay, this is 3/4 plus 1 over 8, right? And I think this is less than 1. Okay? And the same goes here, this is less than 1. Okay, but then a non-prefix code can be anything, right? Okay, so what I mean by anything is that it can be something like this. Codes, okay, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0. Okay? No. That's another example. Okay, it can be like this. Codes 0, 1, 0, 0, 0, 1. Okay, suppose it is something like that. Now if this is the case, then okay, let's try this. Okay, so this is 1 over 2 plus 1 over 2, okay, plus 1 over 4 plus 1 over 4, correct? And the result here is more than 1. Okay, now I can come up with this example because a non-prefix code, it can be anything, you see. So as you can see here, this 0 is a prefix of that, this 1 can be a prefix of that. But a prefix code, if we want the code to be prefixed, then it is a bit more constrained. And so this is in fact a very important relation in as far as prefix code is concerned. Okay, we have this important, okay, in the textbook they would state it as a theorem. See? So we have this, okay, Okay, for prefix code and prefix code only. Okay, this summation. Okay, what is that? Okay, now that is 1/2 L. It will be less than or equals to 1. Right? So keep this in mind. Okay, so we come now to the question of what exactly is the relationship between average code length, okay, average code length, and the entropy, okay, the entropy of a coding system. Right. Now, average code length, we have seen okay, what this is, and the same goes for entropy. The question now is HS, if we minus from HS L average, shall we get 0? Is it more than 0? More than or equals to 0? Is it less than 0 or less than or equals to 0? So this is the question. Okay, right. Now L average, okay, what is it? Okay, L average, okay, we have seen that it is equals to summation probability of using a particular code, okay, times the length of that code, right? And HS, what is HS? HS is this particular summation, okay, negative summation probability of using a particular code times the logarithm of that probability, right? So what is the relationship between these two summation? So that is the question. Okay, so we're going to do some mathematical manipulation for this. Okay, so here we go. Okay, I'm going to use a different ink, different color. Oops, okay, never mind. HS minus L average, okay, and HS is equals to this, right? And L average is equals to P probability times length. Okay. Okay, what do we have here? We can combine the summation. Okay, that might make things more convenient. It is right. LGPI minus LI. Okay, and oops. Okay. All right. Okay, so I think this should be positive, right? Because we bring out the negative here, so inside here should be positive. Right, so we continue now. Okay, what do we have now? Alright, so this is logarithm, this is no logarithm, but I can easily make a logarithm appear there. Okay, equals to minus pi logarithm pi plus, okay, just do this, logarithm to base 2 to the power of li. Okay, this is the same. Okay, it is the same as this. Alright, okay, now okay, so the reason why I want to do it this way, because I want to make this the logarithm appear there, then I can combine these two together. Okay, so what I have next equals to okay, let's see. Okay, so this is what we have. Okay, we combine the two logarithms together. This is basic logarithm arithmetic. Okay, so you can look up on this stuff if you have forgotten about it. So logarithm of these two logarithms we can combine together. We just multiply their arguments together. Okay, so P probability times 2 Li. Alright, so this is what we have. Now, how to deal with this? Right. Okay, let's see. Okay, this is the same as, okay, if we bring this negative inside the logarithm, then okay, the result is this. Okay, summation probability. Oops. All right. Okay, so logarithm 1 over probability I to Li. This is what we have right now. Okay, is this telling me anything at all? Okay, what can I say about this part here? Now, I have been doing some numerical experiments in a spreadsheet, okay, to understand a bit more about logarithm. Okay, what is the relationship between x and its logarithm? So as you can see, in one column we have x, and in the other column we have logarithm of x. Okay, I can see some numbers here, and what can I say about these numbers in relation to its corresponding values for x? Okay, I plot all this, and okay, let's see what I have now. So this is what I have. Now, okay, what can I say about the relationship between x and log x? Well, certainly it seems that x is always more than logarithm x, right? Okay, but there is a gap here. So I'm going to retry this with x minus 1 instead of x. So this is my table now. I add another column for x minus 1. Okay, and I shall plot this again. So what will I get? Okay, so this is what I have. So I plot this actually in Google spreadsheet. I think it looks nicer than the other spreadsheet that I have been using. Right, okay, so never mind. Okay, now let's take a look at what we have here. So, okay, x minus 1, oops, sorry. Okay, so x minus 1 is the blue one, and logarithm x is this. Now, we can see something here, right? We can state a stronger relation now. Okay, now, and we have this. Okay, logarithm x is always less than or equals to x. But of course, this sort of relation, it can be formally proven, and I think it might be in your textbook, okay? A formal proof of this. No, sorry, minus 1, alright. Okay, so logarithm x is always less than or equals to x minus 1. Right, so what can we do with this new knowledge? Right, we go back to this particular derivation. Okay, so we can continue. And what do we have? Right, this last relation, okay, this last form, okay, we can say that it is, okay, let me rewrite it. b to li, it is less than or equals to summation of pi, okay, 1 over p I to li, okay, that should be an I there, okay, minus 1. Okay, right, can you see this? Okay. From the relation that we have seen in the previous slide, so we can now state this, right? Okay, so what is this thing here? Okay, equals to summation pi. Okay, so I can just bring this pi into here, then cancel, what I get? Okay, 2 li, okay, this should be I, right? Minus pi, right? Can you understand this? Okay, now let's continue. So we have, okay, now, right, this summation, what, have you seen this before? Okay, so now this part here is 1, right, minus 1, because summation of probability, okay, in the coding systems that we assume, okay, it is always equals to 1, right? Now this part here, have you seen this before? Okay, so this is, remember that when we were discussing about the properties of prefix code, this summation will always be less than or equals to 1, right? So 1, and this thing, okay, as I said earlier, this is minus 1. So in other words, 1 minus 1, we get 0. And going back, okay, to the start of this derivation, It means that these, oops, sorry, okay, HS minus L average, it is less than or equals to 0. Can you understand this? Or we can also put it as HS is less than L average. So this L average is the average length of our code, and this HS describes the property of the input. Okay, the properties of the entropy of the input. And what it means is that this is the lower bound for the length of our code. Okay, the length of our code cannot be less than the entropy of the input text. Okay, it can be equals. Okay, that would be the lower bound, right? And so finally we come to the Huffmann code. Anyway, thanks for still being here, right? So what is this Huffmann method? It is an algorithm for building. It is actually an algorithm for building a binary tree that represents an optimal prefix code. Okay, so we're going to look at an example. Okay, suppose we have the following probabilities. Okay, so these are the probabilities for the unique strings in our input text. Now, first of all, make sure that you write them in an ascending order. So as you can see here, 0.1 is the lowest and 0.4 is the highest, right? Now, imagine that we associate with each of these a node. Okay, so this node comprises by itself a complete tree. Okay, but it's just a root. Now, consider the two lowest probabilities. Get the nodes associated with the two lowest probabilities. So as you can see, they are the ones with the probabilities 0.1 and 0.2, right? Alright, merge these two trees together like this. Okay, so the new tree, it has a root, and this root we need to associate with it a new probability, and that probability is the sum of the probabilities of the leaf nodes. Okay, so we have 0.1 plus 0.2, that will give you 0.3. Can you understand this? Alright, okay, we continue now in this manner. Okay, so just look at the roots of the just look at the roots of the trees. Okay, so for this particular tree, we have the node with the probability 0.3, and we have these two other trees. Okay, each of which comprises of just the root, right? Now, look at the two lowest probabilities. Okay, just look at the roots of the trees and find the nodes associated with the two lowest probabilities. So as you can see that it is these two, right? This node and this particular node. Now, form a new tree in this way. Okay, so we have a new node, and the probability associated with that new node is 0.3 plus 0.3, and that will give you 0.6. Can you understand this? So now we have two trees, this tree, big tree, and this single node tree, right? So we look at the root of this big tree, which is having a probability of 0.6, and we merge it with the node, with the tree that comprises of just a single what do you call that? Okay, one more. Single root. Okay, why can I undo this? Okay, never mind. Right, so we form a new tree like this, and of course the root of this overall tree, the new tree, okay, this is the complete tree. Okay, the probability associated with this is 0.6 plus 0.4, that will give you 1. Okay, can you understand this? Well, something happened and I lost my tree, but I have redrawn the tree, and this is what we have right now. Okay, so what I'm going to do now is that I'm going to label this tree, and I'm going to label it such that the left edges are all labeled with zeros, and the right edges, which means that the edges that go to the right, okay, I'm going to label it with ones. Okay, so let me show you how this is done. Okay, we start from the root. Okay, this is the root. So the left edge label it as 0 and the right one label it as 1. Okay, so we go in the same way for all the other nodes: 0, 1, 0 and 1. Okay, so finally this is what we have. Now, what is the prefix code suggested by this binary tree? Okay, so we look at the leaves. So these are all the leaves, right? 0.1, 0.2, 0.3 and 0.4. Okay, now consider the path from the root to this particular leaf. So the path, I shall mark it out like this. Okay, and note the label on the edges along the path. Okay, can you see that? So what we can say here is that for the string having a probability of 0.1, okay, the binary code shall be 0, 0, 0. Okay, so this is a probability and this is the code, right? And consider now this particular leaf that is associated with the probability 0.2. The path from the root to it is this. Okay, so look at the labels on the edges. It is 0, 0 and 1, correct? So it means that the string with the probability 0.2, we label it with 0, or we encode it with 0, 0, 1. Can you understand this? Now consider now this 0.3, okay, the node with the probability 0.3. The path from the root down to it is this, right? So again, look at the labels 0 and 1. So in other words, the string with the probability 0.3, okay, we should encode it with the bit string 0, 1. And finally we come to this 0.4, and there's only a single edge from the root down to it. So you can guess, right? For 0.4 probability, the bit string is just a single bit, which is 1. Right, and so this is the coding system suggested by Huffmann method. Okay, this is what we can derive applying the algorithm. And the first question is it a prefix coding system? So we have to check the codes. Now, 001, is it a prefix of any other code here? Nope. 000 is not a prefix of any other code. Now 001 here, is it a prefix of any other code? No. 01, no. 1, no. So in other words, this coding system derived through Huffmann algorithm, it is a prefix coding system. The next question is this coding system an optimal coding system? Okay, so let us calculate the average length of the codes here. Okay, I'm going to move this down and do the calculation up here. Right, so we have L average is equals to, okay, look at the first code. Okay, the length here is 3 and the probability is 0.1, correct? So 0.1 times 3. Okay, we continue ahead. Okay, for this thing here, okay, for this part here, it is, okay, the length is 3. So 0.2, the probability times the length 3. So we continue, and this is 0.1, the length is 2, the probability is 0.3, so we have here 0.3 times 2, and finally 0.4 times 1. And summing it up, okay, you think we'll get 0.6, 0.6, okay, 1.2, 1.5, 1.9. Okay, am I correct? Right, we calculate now the entropy of the input text. So these are the probabilities associated with the text. Okay, so these are the probabilities. Now we calculate the entropy. So do you still remember the formula for that? Okay, so we have HS equals to, okay, so we should be minus summation of the negative probability times logarithm probability. Still remember? It goes like that, right? So we have here negative, okay, the first probability is 0.1, so 0.1 logarithm 0.1, Then we go on with the next probability, okay, which is 0.2 logarithm 0.2 minus 0.3 logarithm 0.3 minus 0.4 logarithm 0.4. And you press into the calculator. So the answer is quite close to 1.9. It's approximately, in fact, 1.9. So we can safely say that the average length is equals to the entropy of the input text. So in other words, this coding system, it is optimal. Okay? Okay, so is the Huffmann method really optimal? Okay, so we need to look at more examples. So this is one example that I did in a spreadsheet. Okay, so what does this table show? Okay, so we have the probability. Okay, so this is the probability, the input probabilities. Okay, so we have 0.1, 0.1, 0.2, 0.3, and 0.3. Okay, and in this particular column, I calculate the entropy. Okay, all right. So the total value for the entropy here is 2.2. Right. Now let's work out the tree for this example. So 0.1, 0.1, 0.2, 0.3, and 0.3. Right. Okay. So right. The two lowest probabilities here is 0.1 and 0.1. Okay. So we assume that each is associated with a single node tree. Okay. Now we merge these two trees, and this is what we get. Okay. So the probability of the root of this new tree is 0.2, right? 0.1 plus 0.1. Now, the two trees, okay, the two trees with the lowest probabilities for the root, okay, we can see that it is this, okay, the new tree, and this, right? So we merge them two together, and the probability associated with this new root is 0.4, right? Now, look at the remaining trees. Okay, this is the new tree, the big one, and these are the two small trees, okay, each comprising of just a single node. Okay, so the two lowest probabilities, okay, we just look at the root. Okay, it should be this, right? 0.3 and 0.3. So we merge them two together, and the root of the new tree that is formed, it is associated with the probability 0.6. So finally now we have just two trees. We merge these two trees together, and we have this, right? And as we have seen earlier, okay, we can associate 0 or 1 with the edges. The one that goes to the left, we associate it with 0, and that which goes to the right, we associate it with 1. So labeling the edges, we have this. Okay, can you see this? Right, and from this big tree, we can see the length of the codes associated with each of the probability. So look at 0.1, the length of the code associated with it is, okay, this is the code 0, 0, 0. The length is 3. So you can see the 3 there. And for these, the length of the path from the root down to it is 3, okay, which means that the length is 3. So you can see the 3 there, right? And for this probability 0.2, okay, the length of the path or the length of the code is 2. You can see the 2 there. And proceeding in the same manner, we have all these values, right? And given the length, we can calculate the probability times the length. So we have all these values, and given all this, we can calculate the average length, and this is what we have. Okay, so the average length, the average length is 2.2. Okay, can you understand this? So is the Huffmann method optimal for this example? Yes, it is optimal because the average length, okay, sorry, okay, so the average length is approximately equals to the entropy. So this is an optimal prefix system, okay, generated by the Huffmann method. Now let's try with more examples. Now we're going to go to a very simple example. Okay, so in this example, we have just a single node, a single probability. Okay, and the probability is 1 because there's only one possible event. In other words, the probability will be 1. Okay, does it make sense here? But let's just do the calculation. Okay, so we have a single probability which is 1, and when we calculate this self-entropy, okay, we're going to get a value of 0. Okay, there's no information in there, right? And the length of the code, it is 0 because there is no edge in this particular tree. Okay, no edge at all. So it means that the average length of the code, it will be 0. And as you can see here, the entropy is equals to the average length. So what we can say is that in the case of a tree, in the case of okay, in this particular example where we have only a single probability, a single event, the Huffmann method is optimal. It is still optimal. Okay. Okay, I tried the Huffmann method with just two nodes, two probabilities, okay, 0.5 and 0.5, and as you can see in this table, okay, so this is the entropy and this is the average length, so it is still equals. Okay, the entropy is still equal to the average length. So in other words, in this particular case, the Huffmann method is still optimal. Right, the question now is, can we prove that the Huffmann method is optimal? Can we prove that it is optimal regardless of the input text, okay, regardless of the input probabilities? Right, okay, let's consider this. Okay, so I'm going to push this to the side, right, and I shall draw the tree for this input set of input probabilities. Okay, so we have 0.1, 0.1, 0.25, 0.25, and finally we have 0.3. Right, so we can build the Huffmann tree for this. Okay, it looks like this. Okay, this is 0.2, right? And this will be 0.45. And once we reach here, so we can see that these two, yeah, they are the ones with the lowest probabilities, so we join them together. We have 0.55 there, and finally we have the entire tree. So the probabilities at the top there, it is 1. Alright, okay, now for this particular case, is it optimal? So we look at the calculations that I have done in this table. Okay. And what do we have here? Okay, so again, okay, this is the entropy and this is the average length. So you can see that in fact it is optimal. The entropy is approximately equals to the average length. So for this particular tree, okay, this is just an arbitrary tree. Okay, think of this as an arbitrary tree. So for this particular tree, it is optimal. Now, okay, now let's say I adjust this tree. Right, the two lowest probabilities in this tree, okay, they are 0.1, 0.1, right? What if I get rid of them? Will the remaining tree be still optimal? Okay, will the remaining prefix coding system be still optimal? So in other words, what I'm saying is that if we get rid of this and we replace this with a single probability 0.2, what will happen? Will the resulting prefix code be still optimal? Okay, let's take a look at this. As shown in the table here, in fact, the resulting prefix system is still optimal. Okay, so as you can see here, initially in the previous slides we had two nodes. Okay, here, okay, and the probabilities associated with each is 0.1, right? But after deleting this, okay, so we only have this node 0.2 there, and we look at the prefix code suggested by this tree. And as we can see in this table, it is still optimal. Okay, this is the entropy and this is the L average. Okay, now what if we continue further? Now look at this tree. Okay, what are the lowest probabilities here? Look at the leaves only, right? So we can see that they are, okay, look at the lowest probabilities. Look at the nodes which are siblings. So you can see that these are siblings and the probabilities associated with them are the lowest in the trees, right? Now what if we merge them together? Okay, get rid of them. In other words, looking at this table here, we get rid of this and we replace this with a single probability with a value of 0.45. Now what will happen? Will the resulting prefix code be still optimal? Okay, let's do this calculation. Well, this is what we have, and as you can see here, the resulting prefix system is still optimal. Okay, so entropy and L average, so they are the same, they are approximately the same, right? The entropy and the L average, right? So it won't be exactly the same because of the numerical precisions involved in calculating the logarithm, but more or less they are about the same. Okay, so in other words, the prefix system, we can say that they are still optimal. It is still optimal, I mean. Now finally we have just two probabilities, okay, 0.45 and 0.55, and the prefix systems, as you can see here, the prefix coding system, it is still optimal. Okay, the entropy and the average length, so these two values are approximately the same, right? Okay, so we can go further. Okay, we can reduce this to just a single probability. Okay, just one probability, which is the value of 1, having the value of 1, and we have seen that for such a case, the prefix system suggested by the tree, it will be optimal, right? We have seen that in a few slides before this. Okay, now what does this suggest to you? Okay, can we try to prove that the Huffmann coding is optimal by means of induction? Can you do a proof by induction for this? Right? So I leave it to you to do this. Alright, so we stop here. Thanks and goodbye.